So today we will see the type of the coordinate system. Okay, I will start now. So there are two type of the coordinate systems used in the matrix methods of structural analysis. The first is, in any structural analysis, there are two type of coordinate system. The first one is the global coordinate system, and second is the local coordinate system. So these two systems are to be used for the analysis of any type of the truss. So first of all, we'll see this. What is exactly meant by the global coordinate system and the local coordinate system. So first, the global coordinate system, there is a single global coordinate system. Okay, like the normal coordinate system, which we are using always. Okay, like x, y, and z. That is called as a global coordinate system. So there is a single coordinate system. The global coordinate system provides a universal set of coordinates that are independent of the component. Okay, means this global coordinate system will never change. This global coordinate system is same for whole structure. Okay, so if you are analyzing a three-dimensional structure, your global coordinate system will be like this. Okay, there will be x, y, and z. These are the coordinate axes: coordinate x, coordinate y, and coordinate z. Okay, if you are analyzing a two-dimensional force system, then there is a x and y. Okay, so this is called as a global coordinate system. Okay, which is a universal set of coordinate and which will never change. That is called as a global coordinate. Okay, so this type of the system you can see in the second, x and y. So this is what a two-dimensional, for a two-dimensional analysis, we are using this type of the system, which is called as a global coordinate system. Okay, and second type is local coordinate system. Okay, so local coordinate system will be depend on the member. So local is also called as a member. Okay, so it is also the local coordinate system or member coordinate system. Okay, so that local coordinate system will be changed according to the member. Okay, but the global coordinate system will never change. Okay, this will be your, you can see in this figure, this is your global coordinate system. Okay, and this is a universal coordinate system which will never change. Then the local coordinate system, you can see in the local coordinate system, there is a local coordinate system for every member. For every member, you will have to assemble the local coordinate system. So from this figure, you can see that x is always from starting to ending along the member. If you see this figure, here you can see x is starting, here you can see this x. Okay, so x is always start to end along the member. Okay, means if your member is inclined member, so always x-axis will be along that member. Okay, x-axis will always be along that member, and that always start from starting node to the ending node of the member. Starting node to the ending node of the member, and y is in the direction of the minor principal axis. Y is in the direction of the minor principal axis, and z is in the direction of in the major principal axis. Okay, But when we are going to analyze a plane structure, like a two-dimensional structure, there will be only Ly and Lx. That means x axis along the member and y axis will be perpendicular to the x axis. Okay. So for a two-dimensional force system, your local coordinate will be local x or local x axis or member x axis. So local x axis is always from starting to the ending of your member. Okay. And that local axis is always acting along the member. Okay. Means if your member is inclined, so local x axis will be acting along the inclined member. Okay, from starting end to the ending end of the member. But if your member is a perpendicular or vertical member, so local x will be acting along that vertical member, and local y will be always perpendicular to the local x. Okay, here in this figure you can see that local x is along the member and local y will be the perpendicular to that member. So this local coordinate system will be always changing for every member. Okay, so there is a local coordinate system for every member. So whenever we are analyzing a plane truss, we'll have to define a local coordinate system for every member. But the global coordinate system, it is a universal set of coordinate and it will never change. Okay, so this is the two type of the coordinate system we are using for the analysis of the structures. Okay, so here in this case you can see there is a global x and the local x coordinate system. Okay, so this you can see this is a global coordinate system, and you refer the second small figure. Okay, that is a local coordinate system. So for example, we'll consider here, consider a planar truss shown in figure below. For each member of the truss, we could write one equation of the type F is equal to K into U. So this relation you know, F is equal to K into delta along its axial direction. Okay, for every member. You can see in this figure, so in this figure you can see for every member there are 6 members in this truss. Okay, so for every member along its axial direction, you can write down the equation of F is equal to K into delta, which is called as a local coordinate system. Okay, so as there is a 6 member, so there is a 6 local coordinate system for every member. Okay, but the global coordinate system is same for whole structure. Okay, global coordinate system will be same for whole structure. Means your x-axis will be horizontal and your y-axis will be vertical. But each member has different local coordinate system. Okay, for every member in this truss, there will be a different local coordinate system. Okay, so what exactly it is that we will again see. But to analyze the plane truss shown in figure, it is required to write the force displacement relation for the complete truss in a coordinate system common to all members. Okay, such a coordinate system is referred to as global coordinate system. Okay, for every member it is required to write the force displacement relation for the complete truss. Okay, so that the global coordinate system will be common to all members. Okay, so that global coordinate system is referred for the analysis of truss. Okay, so these two type of the force system we are using for the analysis of the structures, local and global. Okay, local means your axis will be along the member or along the local direction. Local means member. Local means member. So your x-axis will always be acting along that member, and y-axis will be perpendicular to x-axis. Okay. So here you can see in this truss, as there is a 6 members, for every member there will be different local coordinate system, because the orientation of the member is different. So for every member, local x and local y will be different. But for this structure, the global coordinate system will be common. Okay, means your global x will be horizontal and global y will be vertical, because this is a plane type structure. Okay, this is a planar structure. So x will be horizontal and y will be vertical, which is called as the global. Okay. Now, if you consider from this figure, if you consider any of the member, and if you want to show the local coordinate system and the global coordinate system, so that we can show. So in the same, in this figure you can see so I have considered the inclined member from the so here you can see this is one inclined member for clear the local and the global coordinate system. I have considered the inclined member, okay, from above truss. So there you can see the first figure A shows you the local coordinate system. Okay, this is a truss element, and figure A shows you the local coordinate system, and figure B shows you the global coordinate system. Figure B shows you the global coordinate system. So where you can see in this member, this is the inclined member. So you can see here x dash. X dash I have written here. So this is a local x, and y dash will be the local y. And this node 1, this is the starting node, and node 2, it is the ending node of the member. So always your local x-axis will be always from starting to ending node of the member. Okay, this will be positive x. Okay, positive x dash. Okay, and y dash will be perpendicular to x dash. So this becomes the local coordinate system for this inclined member. Okay, so if in any case, suppose the 2 is your starting node and 1 is your ending node, then your local x dash will be from starting 2 to ending 1. So that starting node and ending node can be changed. So always you have to keep in mind that your local x is always from starting node to the ending node of the member, and it will always acting along the member, and y will be perpendicular to the x-axis. Now in the second figure B, the same member is considered, and here it is shown the global coordinate system. Okay, means the displacement for this member in the global direction, it is shown here. So this is X and Y. This is a global coordinate system. This is for complete structure, complete truss. This will never change. But your local coordinate system will change for every member. Okay, and here you can see that this U1 dash and U2 dash. Okay, this U1 dash and U2 dash, these are the displacement along X direction. Okay, and as you know that in case of the plane truss, there are only the axial force. So there is only the axial displacement. So in the local direction, there is only this U displacement along this X direction. Along Y direction, there will be no displacement because force is axial force. Okay, but in the global coordinate system, you'll have to show the displacement along X, along horizontal X, and along vertical Y. So here in the second figure, you can see that at node 1, U1 is the displacement along X and V1 is the displacement along Y. And at node 2, you can see U2 is the displacement at 2 along X direction and V2 is the displacement along 2 along global Y direction. Okay, so in the global coordinate system, there will be 4 displacement component for each member, which will be shown along global X and global Y direction. You see this reference, this X and Y axis. But in case of the local direction, local coordinate system, there will be the displacement at this node 1 and node 2 along only X direction, along that member. Because in this case, we are denoting or we are showing the displacement in the local coordinate system. But in the second figure, we are showing the displacement of that node 1 or node 2 in the global coordinate system. Okay, so here in this member, there is only 2 component of the displacement, U1 dash and U2 dash along X direction. But in in the global coordinate system, there are 4 displacement component along node and node 2. That is U1, V1, U2, V2. So this is the difference between the local coordinate system and the global coordinate. Okay. So what you have to keep in mind here, local means member. Okay. Local means local axis or member axis. Okay. So local X will be always from along the member. And global means this system being along X and along Y. That will be your global coordinate system. And this theta you can see, this is the angle between the global X to the local X. Theta is the angle between global X to local X. So why we are using this system in this in the method, in the matrix method? Because whatever the structure you have to solve, that you have to solve in the global coordinate system. Okay, so that you have to replace that system from local to global coordinate system. So that's why we are using this 2 coordinate system for the analysis of the structure. Means using the various matrix, we can transfer the displacement or the force from local to global or global to local. Okay, so that's why you should know the meaning of the local coordinate system and the global coordinate system. Okay, global, only what you have to keep in mind here, you see this figure, you in the this figure you can see this one Lx Ly, this shows you the local coordinate system, and here you can see the this x and y, this shows you the global coordinate system. Okay, so this is the difference between local and global coordinate system. Okay, so always we are using for the analysis of structure, always we are showing the displacement or the force component in the global coordinate system. So for that, if there is a local coordinates, or if you're having the local displacement, you'll have to convert that displacement to the global displacement, or local force to the global force. So for that, or to understand this, or for that to assemble the stiffness matrix, we'll have to see these some derivations, okay, which will explain you how to transfer the force or the displacement from local to global coordinate system, okay, or global to local. So this is the important topic. That means what is exactly the local and the global coordinate system. Okay, so I hope that you should understood this local and difference between local and global coordinate system. So from these two figures, it will be understood. So here I have considered one sample member. I have considered inclined member. Okay, if you consider the this truss, okay, if you consider any vertical member or horizontal member, so if you consider this vertical member, okay, so for this vertical member, its local x-axis will be from its bottom node to top node. Suppose bottom node we will consider starting node, at top node we will consider the ending node. So your local x will be from bottom to top, and local y will be perpendicular to x. So similarly, for horizontal member, local x will be from this left node to right node. Okay, local x, and local y will be perpendicular to that. So likewise, the local coordinate system will be different for every member, but your global coordinate system will be same for whole structure. Okay, so always your global coordinate system will be like this. So now we will see the derivation. We have to take the three derivation here for assembling the stiffness matrix, and that stiffness matrix will have to use for the solving of the problem. Okay, and also with the use of this derivation, it will be clear to you what exactly the local system, local coordinate system, and the global coordinate system. So first derivation we will see, because without this derivation we cannot solve the problem, or we cannot analyze the truss. Okay, so this is the first derivation I will take. Okay, so this is the derivation of the local stiffness matrix for bar element. Okay, local means member. Okay, so using from this derivation we will find out the stiffness matrix for bar element, means truss member. We'll consider any truss member, and for that truss member we will derive the stiffness matrix along the local direction. Okay, along the local or along the member, local or member. So this derivation, it can be asked in this way also. Derive the elemental stiffness matrix for plain truss along the member axis. Along the member axis or along the local axis. Okay. So that is the derivation of elemental stiffness matrix along the member axis. Okay. Or it is the derivation of local stiffness matrix for bar element. Okay. Local means we have to assemble the stiffness matrix for any of the member along the local direction, along the local or along the member axis. So for that, and that stiffness matrix will be same, only the direction will change, local direction change, but the stiffness matrix will be same. So we will consider any of the member of the truss. So here I have considered this bar element, or we can say it is the truss member. Okay, so consider a bar element as shown in figure. You can see this figure. Okay, you just concentrate on this and try and understand the local coordinate system. So here I have considered this member, and I have shown this member is horizontal member, and I have shown here local x-axis x, or you can write it as LX. So let the A will be the cross sectional area, E will be the end modulus of the material, and L is the length of the member. Okay. So let starting node be 1. You can see here the starting node be 1, and the ending node of this member will be 2. Ending 2, and U1 and U2 be the displacement of truss members in local coordinate system along x-axis. Okay, U1 and U2 generally for local coordinate system are the displacement are denoted with these small alphabets. Okay, so U1 and U2, these are the displacements of the truss member in the local coordinate system along x-axis. Okay, so as you note that there is an axial force in the truss member, there will be only the axial displacement. There will be only the axial displacement, no other type of the displacement. Okay, so in the y direction, the displacement will be 0. So that's we are not shown here. So that's why we have considered the U1 and U2 be the displacement at node 1 and at node 2. So this is what just I have imagined that the under the action of the external loading, the members of the trusses will get deflected from its original position to the final position. There will be some deflection. Okay, so it is not necessary to show the deflected shape of the truss, but only we have to assume it. So here what we have assumed, after deformation at node 1, there will be the U1 displacement. Okay, along which direction? Along x direction, because we have to assemble a stiffness matrix in the local direction. Okay, and U2 is the displacement at node 2 along the same direction. Okay. Hello. Can you see the screen?
Yes, ma'am.
Member elemental stiffness matrix. Member elemental stiffness matrix. So member elemental stiffness matrix. Can you see the screen? Member elemental stiffness matrix. Yes, you can see.
No, ma'am.
Which screen you can see? Member elemental stiffness matrix. Derivation of local stiffness matrix. Okay. Now I'm changing this. Can you see the second slide?
No, ma'am. No.
Member elemental stiffness matrix.
Ma'am, you are not audible. Hello.
Hello. Hello. Hello.
यस मैम
Hello.
आवाज आ रही है।
ठीक है आपको? Member elemental stiffness matrix. Member
यस
elemental
मैम
stiffness matrix.
विजिबल है।
Okay. So in the first, assuming node 2 is fixed and node 1 is free to deform. So in this figure, you see that in the first figure we have seen the node 1 and node 2. Both are free. Okay. Where we have assumed U1 and the U2 displacements are at node 1 and at node 2. So now we will assuming node 2 is fixed and node 1 is free to deform. Okay. So here you can see that I have fixed this, means I will not allow any displacement at this second node, and this node 1 will be free to deform. Okay, so let apply displacement u1 at node 1. Okay, let apply the displacement u1 at node 1. So nodal force at node 1 is, at this node, the nodal force at node 1 is Fx1 is equal to AE by L into U1. So in the last class, we have seen this relation F is equal to K into delta. Okay, F is equal to K into delta. And where K is axial stiffness coefficient for truss element. And that K value we have find out AE by L. That we have already done. So K is equal to AE by L. Just that AE by L value is written here. So this nodal force, this is in the term of force and displacement relationship. So you can see that Fx1 is equal to K into delta. So delta is U1 here and K is A by L. Okay. So this is the force we have written in terms of K and delta. Okay. So nodal force at node 1 is given as A by L into U1. Nodal force at node 1 is A by L into U1. Okay. How much displacement we have assumed at node 1? It is U1. So delta we have replaced is U1. And K we have replaced is A by L. A is replaced as A by L. So nodal force at node 1 becomes A by L into U1. Okay. From the equilibrium of the element, the force in node 2 is, okay. So here the force direction, that force direction is along this member, along x direction. X direction. So this force will be along the x direction. So at this other node, same force will be applied, but will be in the opposite direction. Okay. So there is every action there will be equal opposite reaction. Every action there will be equal and opposite reaction. So I have shown in the second node, I have shown this direction with the same, but the magnitude Fx2. So this is from equilibrium of element. The nodal force in node 2 is Fx2 is equal to minus A by L into U1. Same force will be there, but it will be in the opposite direction. So direction I have not changed here, but magnitude I have written here. Okay. So this force is the type of the compressive force. Okay. So Fx2 is minus A by L into U1. And this is we can see from the equilibrium of the element. Okay. So same force will be applied at node 2, but will be in the opposite direction. Okay. So Fx1 will be equal to A by L into U1. Fx2 will be equal to minus A by L into U1. Fx2 will be equal to minus A by L into U1. So this is equation 1 and equation 2. Then second, assuming node 1 is fixed, you can see in this figure, node 1 is fixed and node 2 is free to deform. Okay, node 2 is free to deform. So there will be the displacement at node 2 along x direction. Okay, so if you allow this node 2 for displacement, so nodal force at node 2, nodal force at node 2 will be Fx2. Okay, as it is node 2, we have written is Fx2 will be equal to A by L into U2, because node 2 is free to deform. So how much displacement we applied at node 2? U2. So we have applied the displacement at node 2 is U2. Fx2 is equal to A by L into U2. So with the similar way, what will be the nodal force at node 1? Okay. So this is assumed, we have assumed the plus A by L into U2. Same force will be applied here. Okay, but will be in a opposite direction. Okay. So here you can see I have not shown the direction, but I have written it a magnitude minus. Means actually this direction at node 1 should be left. Okay. So here you can see the nature of the force is the tensile. Okay. So the nodal force at node 1 is minus A by L into U2. Okay. So displacement we have assumed is U2. So in both the case, same force will be there, but will be in the opposite direction. So sign is minus. Okay. So at node 2, Fx2 is equal to A by L into U2. Fx2 is equal to A by L into U2. Okay. And from the equilibrium of the element, the force in node 1 is Fx1, which we have denoted is Fx1, is equal to minus A by L into U2. Okay. So concept is that we have considered a single member of the truss and we have denoted its displacement U2 and U1 and U2 at node 1 and node 2, and then one end we have keep the fixed and other end is free to deform, and we have applied the displacement U1 at node 1. So from this, F is equal to K delta relation, as K is equal to A by L, we got the nodal force at node 1 and node 2, because we are interested to find out the force in the member. So that force you can get from the relation of K into delta. And if you know the value of K and if you know the value of delta, you can find out the force. Okay. So from the first figure, we got the values of Fx1 and Fx2. Then we have keeping the node 1 as fixed, and we have node 2 we have assumed free to deform. And from again, we have applied the displacement at node 2 is U2. We have applied the displacement as U. So whatever the relation you will get, that is in terms of U2. Okay. So at node 2, you will get the nodal force Fx2 A by L into U2. And node 1, as it is plus, you will get minus. Okay. So these are the equation 1, 2, 3, and 4. Okay. These equations we are having. Now in the next slide, we have to assemble the member elemental stiffness matrix. So from that member elemental stiffness matrix, we will get the stiffness matrix along member axis. So here you can see the member elemental stiffness matrix. Okay, so third will be equation of member end forces. So that elemental load can be superimposed to get the total member end forces. Okay, so add fx1 from equation 1, 2, 3, 4. We will add fx1 is equal to A by L u1 minus A by L u2. Okay, will get the total member end force at node 1. Okay, total member end force at node 1, that is denoted by fx1, which is equal to A by L u1 minus A by L u2. In the similar way, we can find out the total member end force at node 2, which is equal to minus A by L u1 plus A by L into u2. Okay, so these two equations you will get after superimposing the total elemental load at node 1 and at node 2. Okay, so these two equations you can write down in the matrix form. You can write down in the matrix form, which is equal to fx1 fx2 is equal to A by L minus A by L minus A by L A by L. Only we will take this stiffness coefficient. Okay, A by L. It is what? This is the axial stiffness coefficient for plane thrust. Okay, axial stiffness coefficient. Okay, so this we have take it common into u1 into u2. u1 into u2. So you can see that after writing this is in the matrix form. This relation, whatever the equation you are getting, that is in terms of F is equal to K into delta. F is equal to K into delta, where F is Fx1, Fx2, which is the elemental force matrix. Fx1, Fx2, elemental force matrix. And this matrix A by L minus A by L minus A by L and A by L. This matrix is called as elemental stiffness matrix. This matrix is called as elemental stiffness matrix. Okay, which is denoted by K. Which is denoted by K, or it is also this A by L denoted by K. It is equal to A by L. And this matrix is denoted by the notation SM. This is denoted by the notation SM. So SM is equal to K minus K minus K, K. This is a 2 by 2 matrix you will get, which is called as the elemental stiffness matrix. Which is called as the elemental stiffness matrix. And this delta is nothing but U1, U2. It is the elemental displacement matrix. Elemental means local or member, which is also called as a local displacement. Okay, so this is the derivation of stiffness matrix along the local direction. Okay, so this K is nothing but the stiffness coefficient. Okay, so this matrix, SM matrix, it is to be used for the analysis of thrust. Okay, so this is a SM stiffness matrix. M stands for member. M stands for member. So S stands for stiffness. So this is a notation used for the stiffness matrix along member axis. Okay, so this SM is nothing but the stiffness matrix along the local direction. Okay, so once you know the value of this displacement and the value of this K, you can find out the force. Okay, or if you know the value of force, if you know the value of K, stiffness coefficient, you can find out the joint displacement, which is denoted by delta or U1, U2. So, in case of the stiffness method, as you know that the primary unknown is always joint displacement. Primary unknown is always joint displacement. So, with the help of this elemental stiffness matrix, and if you know the force, you can find out the displacement value. Okay, so that's why first of all you should know the elemental stiffness matrix in case of the plane truss. And always you keep in mind that in case of the plane truss, there is only the axial displacement because there is a axial force, so there is only the axial displacement. So as there is axial displacement, there will be the axial stiffness coefficient will be considered for the calculation, which is equal to A by L. Okay, and this matrix we got after the derivation of this by considering a simple member, and this matrix will be applicable for every member in the structure only for the stiffness matrix along the member axis. Okay, so this is the first derivation. Okay, where we have find out the stiffness matrix along the member axis. ठीक है, तो ये डेरिवेशंस आपको पढ़ना पड़ेगा और ये इसका यूज अपन करेंगे फॉर द सॉल्विंग द प्रॉब्लम. So understood? Am I audible? Understood
Yes,
up to this? क्या देखा अपन ने आज के क्लास में? लोकल कोऑर्डिनेट सिस्टम. हेलो.
yes, ma'am.
ओके, तो आज मैं आपका अटेंडेंस जो है वो मैं क्विज डालती हूँ अभी थोड़ी देर में, तो वो मैं क्विज से आपका अटेंडेंस मार्क कर लूंगी आज. हेलो.
Yes, okay, ma'am.
ओके, तो मैं क्विज दे देती हूँ
Okay,
आपको
ma'am.
थोड़ी देर में, तो वहीं से अटेंडेंस आपकी कंसीडर हो जाएगी. ओके, सो नाउ यू कैन लीव द क्लास. आई गिव द क्विज बेस्ड अटेंडेंस बेस्ड ऑन द क्विज. ठीक है.
Yes, ma'am.